I mean, this is it. Your calculator would tell you what this looks like. But this is it until 6 seconds. Till here. Is it at the maximum height there? No, it's just where the engine's shut off. It's still going upwards after this. When you know, there's things to look for in the problems that are going to help guide you as to what it is they're getting at. Some of them are obvious because it's a situation that you've kind of seen before, or a situation that has marked points of comparison to other situations you've seen. Mass against a spring, one object smacking another object, and them joining together or bouncing apart. There's stuff that we've seen. And then there's problems like this one, which maybe don't fit any one of those molds directly. This problem that you're looking at, of them, one of them is just, is there calculus in the basic function that you need to use that's being called upon in the problem? For example, the very first question does actually ask for you to find impulse. Impulse is already calculus. I mean, it already has explicit in its formula, the integral. You're summing up over the time how the force caused an object to change its momentum. So any problem where we have an explicit formula that is already suggestive of calculus, you might have to do the integral or take the derivative. I know that's a duh, Mr. Shelton, but it's not always as simple as that. It's not always as clear-cut. Because the other thing to consider, which is something that you guys who are inexperienced may not consider, is that every function written as an integral can be written as a derivative. That's not something everybody knows, but it's always there. Any good student of calculus understands that this function has a derivative version too that says that force is equal to dp dt. That's the derivative version of this function. And if you don't know that, well, now you do. All functions that have an integral in them can be written as a derivative. So even if we take, say, this one, which talks about work. Well, it says work is equal to the integral of f dot dr. If you strip away the integral sign, you just put a piece of work that was done. A small amount of work was done because an object was moved by a force a small distance. And then you divide and you find out force can be found by doing the derivative of a work function with respect to position. Would that ever come up on the exam? Well, probably not. But again, if it's not an explicit function that requires calculus, there is an implicit part that applies or suggests calculus. But of course, there's always that when we get putting also the cold facts that acceleration is defined as a derivative. The third thing I think you should think about. So maybe it's not an explicit function, maybe it's not an implicit function, but it could be a definition. Acceleration is the rate of change of velocity. That is an explicit definition for acceleration, just like velocity is the rate of change of position. How do you know when to use calculus? Well, when you're asked for one thing, but they gave you a different function, and you have to change your function. But then also, there are people who actually asked throughout today, 3rd and 6th period, doing this graph together. This one is clearly, from the very beginning, it is a motion equation problem. For the simple fact that they gave an expression for the acceleration as a function of time. They gave you a motion equation. That doesn't mean that's what it's all about, but they gave you a motion equation. So I said to the student that there are 3 things you could look for to determine whether you really need to lean into the calculus for a question. And this, why couldn't we just use motion equations? And I didn't want to say something really rude, but the truth is, it's clear why you can't use motion equations. And when I say can't, what I mean is you can use motion equations. They gave you a motion equation. What they really meant to ask is, why can't I use Galileo's motion equations? Well, for most of this, you can't. Because Galileo's motion equation suggests what? Go ahead. A constant acceleration. For any acceleration that is not constant, you can't use it. You could derive it if they gave you a function, but you can't use it. So let's take a look at working through some of these, because I think some of you probably did okay. Raise your hand if you got. So when it says calculate the magnitude of the net impulse, a lot of words there, but we have a definition for impulse. This is the definition. Now, we don't have in this problem an expression for force, but we do have an expression for acceleration. Since we have an expression for acceleration, we have an expression for force when we just multiply the expression for acceleration by m. Now, this isn't an explicit force. This would be the net force acting on the object, because we know it's acceleration. So my method for doing this problem was to consider that we're looking at the net impulse on the object, and therefore the total change in momentum from 0 to 6 seconds. It's not the only way you could have done this. In fact, in this solution set, they gave lots of alternate solutions. For example, the mass didn't appreciably change. They say it in the problem. So you could write this as m times delta v, which would mean finding an expression for v. We did this first semester. This is a first semester problem. This is a first month problem. This is like a September problem. In fact, you had this problem as a homework question way back then. It was phrased differently. I didn't ask about momentum and I didn't ask about energy, but I asked about all the other things. I did it this way. They're largely the same, but I did it this way. I think some people tried to do it this way. And I think some people did not this at all. So to do it this way, I went ahead and subbed in m times k minus L t squared dt, evaluated from 0 to 6 seconds. They gave us m, k, and L. We can put those in later. When you take the antiderivative, you're going to get mkt minus ml over 3 t cubed, evaluated from 0 to 6. Does anybody need me to do the calculus here? Okay. They gave us an expression to use, they gave us values to use for m, k, and L. So you plug in those values at 6 and plug in those values at 0 and subtract them, and I believe you get 18 Newton seconds for the impulse. So this is the change in momentum or the impulse. Any question about that? Now, whether you found a function for the velocity, which would have been kt minus L over 3 t cubed, or you did it this other way using just the definition of impulse, you're doing the same calculus work. However, you had to find the velocity too. So although this was question A, question B wanted the velocity. For me, that was just taking this and dividing by the mass of 0.5, because I just said this equal to m delta v equals 18 Newton seconds. So delta v was 36 meters per second. Not really sure why they asked B. They gave 2 points for B and 2 points for A. I think together they were trying to point you somewhere, because they clearly wanted you to do something else later on. But you could have gone back to this function and put in 6 for this function and found, of course, that it's 36. Any questions there? All right. Part C, number 1, wanted you to find the kinetic energy of the rocket at the 6-second mark. So if you have a velocity, even if it's the incorrect velocity, you should have been using it here. So you should get full credit if you did all those things. Of course, it is best to use the actual answers and get the right answers. That tends to be how you score points. But 324 joules of energy. It's question number 2 of part C that I think makes us go back and consider what they're asking. They want the change in the gravitational potential energy. Where'd the rocket start at time 0? All right, so it starts on the ground, right? And the engine fires, but it's on the ground. At time equals 0, position equals 0, velocity equals 0. Acceleration equals 9 meters per second squared. How do I know that that's the acceleration at time 0? Right, just plugged it in right here, right? Put in 0 for t, we get left with k, so at time equals 0, the acceleration was 9. So it's experiencing acceleration, and it does so, but that acceleration is becoming a smaller and smaller number over time, right? That's exactly what this says. So eventually, after 6 seconds, the rocket's height has changed. At this moment, its velocity is 36 meters per second. But we don't know how far off the ground it is. We're wanting the change in gravitational potential energy, but we're really looking for whatever the change in height was. Well, we have an expression for velocity, which means we could use it to find an expression for position. Right? You have velocity as a function of time. Take the antiderivative and find the position as a function of time. I don't know what the disconnect is here, but you had an expression for velocity as a function of time. So I'll find y as a function of time, which is just k over 2t squared minus l over, well, this is still a polynomial, so I raise that to 4. Now I divide by 4 times 3 is 12. So this is my function for position. I know I have to add a constant, but that constant is the location of the object at time equals 0. Where is the location of the object at time equals 0? 0. That's right. So although I had definite integrals before, I did an indefinite integral here, but I knew the boundary condition. So you plug in 6 seconds and you get 135 meters. This isn't the answer, but you needed this to figure out what the answer would be. When you plug it all in, I think you get 675 joules of energy. The rocket engine shuts off at 6 seconds. And so the next question is, calculate the maximum height of the rocket. The rocket doesn't just stop, right? So whatever velocity you found earlier in the problem is the velocity the rocket has when the engine's cut off. Is the rocket accelerating when the engine's cut off? Did gravity turn off? Okay, so do we have an answer now? You understand what I'm getting at, right? So at the moment the engine's cut off, we have a velocity of 36 meters per second and an acceleration of 10 meters per second squared downwards. But it doesn't just stop. It continues to go upwards until its velocity, its final velocity is 0. But now it's accelerating. So you have a couple of options on what you're going to do next to find the maximum height of the rocket. You could do say a v squared minus v naught squared equals 2a delta y. We could use this now. Now we can. Because once the engine's cut off, the only force acting on the rocket is gravity. It's providing a constant acceleration. You could use this to figure out how high the rocket goes. I didn't do it this way because they're telling me how they want me to do this. Do you see what they're telling us to do? They just made you find the kinetic energy at 6 seconds and the potential energy at 6 seconds. So right now you know the total energy of the system is the potential energy plus the kinetic, which is 324 plus 675. That's the total energy of the system. I just got to set that equal to mgy max. Now tell me how high the rocket goes. I mean, they're screaming it at us, aren't they? This is why I'm a little bit frustrated, because this one, I mean, if you found the energies, this one was right in your face, because you're just one step in y equals 200 meters. Maximum height of the rocket. But you could do it this way. But this won't tell you 200 meters. This is going to tell you like 67 meters or something like that. 66 perhaps. You have to add that to where the rocket was in order to get the total height from the launch pad. I'm sure you'd lose a point if you didn't do it that way. So this part hurts. This part hurts a lot because you guys, I know I say this once in a while and I know you think I'm being cruel. I'm not. You're not thoughtful about this. You're guessing. They want velocity as a function of time. And they tell you, they put a point in here. And you should use it, right? Where it's at the top. They tell you this is the time when it's at the top. You can make your own point, but there's really no need. Did you put it in your calculator? If you got a velocity function, did you put it in your calculator? Do so right now. If you did, it's still in there. If you didn't, do it now. You have a velocity function. I want to see that you could just take a moment and put it in your calculator. Kt minus L over 3 t cubed is our velocity function, but K is 9 and L is 0.25. Put it in there as intended. I want to see that you can. Some of you do knee-jerk things. We know the velocity is 0 at time 0. Is the velocity ever 0 again? Yeah, when? At the max height. Right, that's where it's 0. That's what you do. That's when it stopped. It has no more velocity. So your graph has to go through the axis twice. And you had to label it. So you know what this one looks like because you could plot it. It's a cube function. And although this is a point of inflection, they didn't care as long as you made it mostly concave down. You had to label this point with your max velocity, 36 meters per second. And then with a straight edge. Had to be a straight edge because you had to make sure the graders understood that the acceleration was constant. So the velocity has a constant slope. Has to be. All righty, folks.